Hello, this is a lecture on model explainability for Data 630. I am Interpretability. So here is the outline of this lecture. So we're going to start with model explainability basics, some importance of explainability, some existing explanation methods that are out there. The scope of explainability you have to define the scope of and to what extent you need to explain the models. An evaluation of explainability, which is another key element similar to the evaluation that we discussed when we fit machine learning models. Evaluation is a key part, an integral part of fitting a machine learning model. So the same applies here for explainability. And we will discuss some desired properties of explanation methods, and we look at some few interpretable models that are out there. There are some models like linear regressions that are inherently interpretable. All right, let's just start with the basics of model explainability. So evaluation metrics such as accuracy, which we studied when we fit machine learning models, they're not sufficient to understand why models perform well on a given task. If you remember, when we feed any model, regardless of the algorithm, the underlying algorithm that we use to train machine learning model, evaluating the metrics using different metrics like precision, recall, sensitivity, specificity, and simple accuracy. Those are the different way of evaluating how the model performs, and but they don't necessarily tell you exactly why the model performs the way it does. So accuracy is not just the way to address the why aspect of the model in question. So another important aspect of, in general, predictive modeling is it is a trade-off between a what and a why. Okay, the what focuses on the prediction accuracy of the model. So if it is a classification model, the accuracy with which it classifies, whatever it is designed to classify. The why aspect, on the other hand, is an aspect of the problem that tells you the underlying relationship of the different variables involved in the data set. So now we can consider an extreme case. Some model can focus on the what, on the prediction accuracy, and then some can focus on the why. But depending on the application area, it's always a compromise between the two aspects of the problem. So a simple example is, if you have a modeling application where it classifies or it detects this customer who's likely to churn, you also would like to know how to prevent that from happening, which is the why aspect of the problem. So it's always some combination of the what and the why. And again, it is also a function of the application area. I'm sure you will find some application where you are not really interested in any aspects of the why. You just want to have a model that predicts accurately. But in general, most application is some balance between the what and the why aspect of the problem. Okay, let's define the word explanation for this context, although the meaning here is not much different from the ordinary use of the word in the English language. So an explanation is in general an answer to a why question. So when you have to explain things, you are answering the why aspect of the problem. So examples are, why didn't a patient treatment work, right? Why a loan application was rejected. So this is the way, when you explain these problems, you are addressing the why question. So in general, humans tend to prefer short and simpler explanations. Now, even when we fit models, we discuss that simpler models are always better than complex models. So now, the extent to which your explanation is simple is also dictated by the underlying problem. So if you have data from a complex domain, then when you try to explain that, the explanation tends to be more complex. When you have a simpler problem domain, the answer you would come up with be rather simple. So, but to the extent practical, you want to make sure that the answer, in general, these explanation models are for human consumption, that we want to make them simpler. Sometimes, if you have answer to a how question, that can also be changed into a why. So it can be rephrased into a why, so you can deal with the why part of it. So, for instance, how alone is rejected with why alone is rejected. So, because explanations tend to be to answer why question, so you want to make sure that how is converted to why. Okay, that's more or less the definition of explanation for the application of explainability in AI or machine learning models. Okay, so this picture, I think it can capture the big picture. So let's start with, you have some problem that is in some aspect of the real world, right? Some application domain, right? And then the assumption is, to a large extent, the phenomenon or the situation in that domain is captured through data. So we collect data through variables and through instances. So we collect over time data that manifests as the real world application, that particular segment of the world. Okay, so that makes your knowledge base. So now you can apply some learning algorithm, machine learning algorithms, and train a model, right? So in this particular sequence, that model, let's assume that model is a black box model, let's say a deep learning model, where you try to encode that knowledge through automation. And so now you have a trained model that mimics that knowledge. Okay, it could be classification, regression, so it doesn't really matter. So what we have is a model that try to capture that knowledge that exists in the data that represents the real world phenomenon. Okay, now the interpretability model, or the explanation method, in this particular depiction is an additional layer to the model that try to provide some understandable logic that a human could consume, right? Instead of the human directly interacting with the complex model, the black box model, which is very difficult to understand, so you are adding a layer that explains the underlying relationship of the model to an extent. Now when we cover later, there is another option where the model itself could do some of the explanation inside as part of the model training, or as part of the algorithm, the training algorithm itself. But in this depiction, it shows there is another layer, this explanation that makes it easy for humans to be able to understand how or why the model was able to make the kind of prediction that it is making. So that's the big picture. This is when we say why this is a place where the model explainability or interpretability is important. All right, so far we discussed about the basics of explainability. We defined the term explainability in the context of machine learning application. Now let's discuss about why is model explainability is important. So we humans have curiosity to find meaning in the world, right? We try to find an explanation for unexpected events. For instance, we try to know why we feel sick. So that is our curiosity, that's in our nature, right? Now, why explain important to machine learning is because we are deploying machine learning solution. We are automating a large aspect of our life, our daily life. That means we need to make sure that this model that we deploy for different application needs to be able to explain things, right? And we need to understand how they make prediction. Now, I think I said this earlier, the extent to which, or the degree to which, this explainability, how explainable the model has to be, depends on the application area. Okay, trivial application, mission critical application. But as we automate most things, it is really important for us to be able to have some level of understanding about the underlying relationship and the mathematical logic, or the logic that allows the machine to be able to predict. Okay. If you have opaque models, another important aspect is, if, let's say, if you're deploying a machine learning model for an important aspect of a problem, or an important problem area where there is limited knowledge, if the machine learning doesn't have any explainability component, whatever knowledge that it is discovered will be hidden to humans, so we won't be able to know or encode that knowledge for future use. It is automated, but the findings remain hidden. And if it is a research area, for instance, some health domain that you want to leverage that information, with opaque models you won't be able to do it. So explainability is an important aspect for that reason. So again, I think I said this probably 2-3 times now. It is really a function of the application domain, right? Some mission critical application, let's say safety critical domains, you need to have explainability or interpretable models. So, for instance, if you know how a self-driving system does its detection of the conflict, then you would be able to know when it fails and to prevent that failure in the future. So you can easily learn or address a weakness of the model if you have that interpretation layer or explanation layer. And also another aspect is, if you have only, you can debug, like when you write a piece of software program, debugging is an important aspect of it. Just you don't even have second thought, you should be able to debug that program. So if we have explanation or explained models, then you would be able to do the same thing. You can debug. You can also do some kind of auditing when you have interpreted layer or explainable models. Another element is explanation helps us to understand the cause of erroneous result during use. Okay, if you know it, you know the kind of logic combination that will lead to erroneous results, so you'll be able to prevent that. So explanation is important for that reason. Now, although if particularly in the future, the direction seems to be model explainability is as important as the performance of model. So there are a lot of APIs, libraries that are being developed now to make models explainable. So in the future, maybe model explainability is an easier extension of the model development process. If that's the case, then there's no harm in deploying or in having explainable models, even for trivial application, right? Because at minimum, it will be able to help you improve the performance of the model if you have that understanding. But the degree to which explainability is important is dependent on the application area. Like I said, mission critical system, you need to have model explainability. So here are some of the benefits if you have explainable models. Now you can ensure fairness, which is an important aspect. Let's say if you are deploying a machine learning solution for loan application process, you got to make sure that you're not, there is no bias, or you're not being unfair to a certain group of people. So that's an important element, right? I think there are a bunch of articles that you can read about misuse or misapplication of machine learning targeting to some groups, partly because the underlying logic was not understood and the model was not explained. There was no easy logic to understand how the model was making the kind of prediction it was making. So there were a number of examples that you can see on the way that unfair models being deployed. You can also, for privacy purposes, you can, if you have explained models, that makes it easier to identify sensitive information that is used in the underlying logic, so you can help ensure privacy. Reliability is another area. If you have explainable models, because of that understanding, you can make it less sensitive to small changes. Causality obviously is a direct application of explainability. You can, by definition, explanation address the y aspect, which is some kind of causal relationship. So you can ensure causality. Trust. In general, we tend, if you understand things, the underlying logic, you tend to trust it. So that allows humans to trust the model. I guess this is a straightforward. Some areas that model explainability is not as critical. If you, let's say, if you are deploying a machine learning model to automate some of your personal chores or activities, that's one area it's not as critical, but it doesn't hurt to deploy it if it is easy enough. Well-studied problems like OCR, optical character recognition, pretty much it's a well-studied, all the underlying knowledge about that domain is known, so explainability is not as important than that kind of application. And this is another one, is potential for system manipulation. Now, if you expose the underlying logic and if you explain every aspect of the model, particularly for some application area like loan application areas, then it could be exploited. A rogue user can get into the explainability aspect of it and be able to exploit the system. So it might be less desirable in areas like that. All right, let's look at some existing explanation methods. This area is still a research area. It is an area being explored, so there are new methods, new way of doing explanation for different machine learning algorithms. But there are some methods, existing methods. So we will discuss 4 different ways of categorizing the groups of explanation methods. So the first one is by criteria. You can categorize explanation methods by criteria, intrinsically and post hoc. So in the intrinsic method, so the way you try to explain the model is by having terms as part of the optimization to penalize the model from being too complex, right? So there will be a dedicated term in the underlying logic, in the underlying mathematical logic, that is being optimized. So the model is being penalized as it gets more complex. So you manage the complex model as part of the training. So that's intrinsic. In the post hoc case, you train the model the way any machine learning you would do any machine learning algorithms, and the interpretation or the explanation is done on the features. So the features that the machine learning algorithm leverage to make the prediction, you try to summarize that. The feature is important. So ranking of the models. Now, when you learn in data 640 about tree ensembles, for instance, some of the random forest or gradient boosting, these are ensemble tree methods. They have out of the box, they have some functionality that you can actually rank features based on their importance for the prediction of the problem. Or so that is post that. So that's when you categorize by criteria. You can also categorize by results. So different way of doing that is you can summarize the feature similar to the feature important, but more general characterization of the statistics of the features, right? How often that particular feature is used, and how much contribution it has, things like that. And also you can leverage visualization as part of that summary. You can get into actually the structure and the parameters of the model. So that's another way of focusing on the result. So also this explanation methods, they can generate data points as part of explaining it. And others that are inherently or intrinsically interpretable models like linear regression. I think I have a slide that summarizes some of these interpretable models. Okay, so another way to classify or categorize explanation methods are by the model types or classes. Okay, if it is, so you have model specific or model agnostic. If you have model specific explanation methods, they tend to be more specific for a certain class of models and tools because they work with the specifics of the model. Okay. For instance, in linear regression, you have weights, right? So the models will focus on the weights. So if you don't have this kind of internals, so the machine learning algorithms that don't have this kind of components, then this interpretation methods don't work. So these are model specific and work only for a certain group of models. If it is model agnostic, it doesn't get into the internals of the model or the underlying logic because they tend to be general. They focus on the inputs and the outputs of the model. So they're general because they focus, regardless of how the prediction done by the model inside, this interpretation methods can actually work with any model because they focus on inputs and outputs. Another categorization is the scope, local. If the explanation focuses on individual prediction, that would be local. But if the model focuses on entire model behavior as opposed to focusing on individual prediction, so that would be global. So that would be a type of categorization by scope. Okay. So this, I haven't gotten into the specific method. These are just general categorization of explanation methods. There are many underlying methods. Some work better than others depending on the application area and the learning algorithms. But like I said, this is an area that is still being explored, and there are a lot of changes. Okay, now let's get into scope of explainability. So the scope is defined in relation to the algorithm employed to train the model. So when we discuss the scope here, it relates to the underlying learning algorithm. Remember, any machine learning has different learning algorithms. So that's what separates one machine learning from another machine learning algorithm. So eventually all they produce models, but the underlying learning algorithm. So when we discuss about the scope here, we're talking about as it applies to the learning algorithm. So there are a bunch, and I am not going to get into, I have a slide for each one of those, but I'm going to quickly go through the different aspects of this. So one is the algorithm transparency, how transparent the algorithm is. One is, we kind of touched on this holistic model of the interpretive, just, looks at the totality. Another one is interpretability on a modular level. You can modularize the model and you can focus on that. And another one, local interpretability for a single prediction, the way we discussed it earlier. And another one is a group of predictions. So let's quickly go through each one of these. So this one is how transparent the algorithm is. So it deals with how the algorithm learns the model from data. So that means you have to have a level of understanding how the model does, what is the logic that the model uses or the algorithm uses to make decision. So it creates an underlying understanding of the underlying algorithm. It's not about the specific model. Like I said, it's not on the end result. Or every algorithm end up producing a model, but the focus is on the underlying learning logic. It's not about the data either. It's not about the individual prediction. Again, focuses on the logic, on the underlying logic. So for instance, linear models like regression, they are well understood models. So they are high transparent models because they are well studied. The algorithm is simple enough to be understood. Things like deep learning, they could involve a lot of parameters. So in general, less transparent, and the common term that people use to characterize this kind of models are black box models. Okay, so that is a scope as defined by the algorithm transparency. Another one is you can focus on the totality of the model, the holistic approach of the model, right? You look at the model entirely, so that means you have to have some knowledge about the trained model, you have to have understanding about its output, and also to some extent you have to have understanding about the underlying algorithm as well, in the data that goes into it. So it's a holistic approach. It is about understanding how the model makes a decision based on its features and components, structure and parameters. But in general, this is difficult because you can't touch every aspect of the model, particularly the structure and the parameters. When it involves a more complex model like deep learning, this method tends to be high. The scope of this method. So that is how you would scope explainability models by holistic model. Another is a modular approach, which is it involves understanding the complete features of the model. As opposed to focusing on understanding complete features of the model, it try to create some modules, so partitioning the model in different modules, and then you can focus on that a certain aspect of the model or a certain module of the model. So example, weights of linear model. So you can focus on one can understand the relationship of a variable that target by holding other features constant. This is a very strong feature of a linear regression model. So that is one aspect, or we can consider that one module. If you have a decision tree model, you can focus on the nodes that are used as a splitting nodes. So if you're focusing, that is, you are partitioning aspects of the model. This approach in general works only for some, because there are some algorithms you cannot just separate from the rest and be able to still work. So it only works for things that you can separate or isolate. For instance, the way the weights are, the way they work together in deep learning model is kind of inseparable, or at least difficult to separate. So this approach may not work. This is I think that we discussed this part already. So this use scoping on single prediction. So the explanation method focus on single prediction, and try to make your prediction or focus the prediction around those. Okay. Again, this is what we call local. In the prediction may only, so since you focus on local, when you look at the specific area, the prediction may only depend linearly on a subset of features. So that makes understanding easier, because you isolated, or you're focusing rather on a local behavior of the model, and that aspect may be easier to explain. All right, so an example shown here is for a specific house. The model output, maybe price, may only depend on its size, right? So it is local just for that segment of the prediction. So so that is scoping by single prediction. You can also scope it by group of prediction. As opposed to be very specific to local prediction, you can group a certain number of instances or prediction together and try to learn from the behavior of that prediction. Okay. And obviously that you can the explanation from each instance in the group can be aggregated. Okay, another important aspect of explanation is evaluation. So remember, whenever we fit a machine learning model, evaluation is part of that process. Okay, you need to evaluate your model. Now, luckily for machine learning model, there are several criteria or quantitative metric by which we evaluate a model performance. Okay, some are unique to the algorithm, but in general we have general methods. But for explanation or the explainability model, there is no consensus. Again, partly because this is an area that's still being explored. So there's no consensus method how to evaluate the explanation logic itself. But some approaches are you can focus on application level. That means the in product should incorporate some explanation, which you can evaluate using the domain expert. So it's an application focused. Human level means you would have user testing as part of the explanation, generating the explanation layer. You may not necessarily need a domain expert to do that. The functional level is earlier discussed, so you can have as part of the learning algorithm logic itself, you can incorporate, or you can constrain by having terms in the optimization process. So the explanation itself is it's an embedded as part of the learning algorithm. So that's a functional level. All right. Now another aspect. So we have explanation methods. They have properties. Okay. Remember the way the explanation is done is through some algorithm. So there is now, if it is as part of the modeling process itself, there in the learning algorithms there is logic that reinforces explainability in the optimization process. If it is a separate module or it's a separate layer, then there is a separate algorithm try to provide that interpretation layer. So we're talking about another algorithm on top of the machine learning algorithm. Okay. So typically an explanation relates, this is just the goal of explanation in general. It try to relate features of the instances with the model outputs in a humanly understandable way. So that's the whole point. So we try to understand why the model made certain prediction. Okay, so we try to relate the logic used in the model to the output that is provided by the model. Okay. You can also focus on the data. The explanation can focus on the data instances. I know we haven't dedicated time on key nearest neighborhood model, but that's instance you don't have really a trained model. The prediction is done during so because you look at the logic is based on neighbors of that instant that you're predicting, so the focus is on the data instances. So some example mentioned here for SVM model method can generate decision tree as an explanation. So this is you will learn about SVM model. This is support vector machine in data 640. So it is a marginal maximizer method or maximization method. So it creates decision boundaries. So you can leverage that decision. You can, have a layer, decision tree layer as an explanation. Linear regression, I think we said this over and over again. It already has an interpretation layer inherent or intrinsically as part of the model. The weights are interpretable in linear models. So this is the general properties of explanation methods. These are specific properties of explanation methods. So expressive power, how expressive is the model. Like, for instance, if it has if-then rules, it's easier, right? More expressive. Translucency this is the extent to which the explanation methods get into the model structure and parameter, right? How much it reveals the underlying or the inner workings of the algorithm itself. Portability is a range of the model which explanation the explanation can be used. So if you can apply that explanation method to different models, then it is more portable. Another one is complexity. That is the algorithm complexity. Now, again, we're talking about the algorithm that is used to generate the explanation, not the model that trained the machine learning model, but the one that generated the explanation method. How complex is the underlying complexity? So that's the property that's important. Another is accuracy. Similar to the accuracy of the model, we want to have a level of accuracy in the explanation methods. When an explanation method explain the model behavior, we need to know how accurate that is. Okay. In general, if the machine learning model has higher accuracy, then you may need to have a highly accurate explanation method. Fidelity is how well the explanation approximates the model prediction, right? If it has a good fidelity, it would be able to explain the prediction well. Consistency is so if you have explanation on between models trained on a specific task, regardless of the underlying learning algorithm used, but you have multiple models, so you want the explainability to have some level of consistency because the model is deployed on the same task. So that refers to consistency. Stability is when you have a model and if for similar instances predicted by the model, the explanation needs to have some kind of stability, right? If it is not stable, even for some instances, it will provide different explanations. So you want to have the good stability. Comprehensibility, this is as it applies to human consumption. So how easily humans can be able to understand the explanation, because the very reason you have explanation layer is to make it easier for humans to understand the output, right? So that is, the goal. So the explanation layer needs to be easier to understand. The certainty, this reflects the confidence of the model prediction. When it says the model prediction means, so when a model makes some prediction, right? That prediction needs to be accounted for. The level of confidence that prediction is accounted for in the explainability or in the explanation method. Degree of importance, so we kind of touched this earlier. This is a characterization of the feature importance. If the method focuses on the output, so feature characterization is a way to explain. So that is the degree of importance. So it's another property of the explanation method. The novelty is if so some type of prediction, some instances are unique or they don't happen as frequent as others. So how does the explanation model deal with this? So the novelty means there are some uncommon instances predicted by the model. The interpretability model should be able to account for those. And another one is representativeness, which is extent of instance coverage, right? So entire model, this is another aspect that we kind of touched on earlier. You have the entire model versus individual prediction. So you want both aspects to be handled by the explanation layer. So you want a large aspect of the model to be handled, but as well as you want to have a level of accuracy on individual predictions. All right, let's get into how we can characterize good explanation. Some of the features by which we determine if explanation is good or not. So we want them to be contrasting. That means what would the prediction be for different set of inputs, right? You want to be able to test the explanation method for different set of inputs. And another one is selected. When we discussed earlier about the complexity of the explanation method, simple versus complex. Simple in general being a preferred method. So we don't need to have the explanation layer to be very complex, trying to account for every intricate details of the data or the model. Okay, so we can focus on few and most relevant aspects of the model. So that's selected. In general, that allows the method to be simpler. In social, again, the focus of having explanation, the reason that we have explanation methods is for human consumption, which makes the environment and the audience important. So who is using the explanation method? Who's targeted by having that explanation layer? So that is a social behavior. The focus on abnormality, and we kind of touched on this as well. The ability for the model to account for features that are unusual or rare. Okay, there is a segment of the domain that only happens so rare. If the model, if the explanation method is not able to provide any context to that, then it is not as good of a method, because they do happen, these things, and then when they do happen, they become so important. So in fact, in modeling in general, there is a novelty. So in some places they're called anomaly detection, in some places they're called novelty detection. So it's an important area of machine learning. So explainability models should be able to account for those. Truthfulness. This is similar to fidelity, which is an explanation, the ability for the explanation to predict an event as truthful as practical. Consistency with a prior belief. So if there is an existing knowledge in that domain, and the explanation method should not, obviously to the extent practical, should not contradict with that existing knowledge. Otherwise, it's going to create confusion, because if the explanation layer provides an interpretation that is inconsistent with existing knowledge, then you have to question the logic used to come up with the explanation layer. Generality, this is a desire to have the ability, or the explanation method to have some kind of generalization ability. It's not easy, but it's a desired property. It can be measured by the feature's importance. So maybe if the method focuses on feature importance, the generalizability is more achievable, because you're not focusing on the components of the model, but on the features that went into that learning algorithm. So it allows you to make the method more general. Okay, so this is our last slide, and this is about some interpretable models. So the focus in this lecture when I discussed about separate layers is for more complex models that are difficult to interpret, right? For those, you have to come up with a separate layer, separate logic to provide that interpretation, okay? But there are some models, existing models, that are easy to interpret and explain, and they don't need any separate module or logic for interpretation. A prime example of that is regression model. Regression models is, one of the things, in addition to provides for some problem area where linear assumption holds, so in addition to providing accurate results, regression, by having those weights, you can actually understand the way the decision was made. So the logic itself in linear regression algorithm is easy enough that you don't need a separate interpretation layer or interpretation model. Another one is a decision tree. You can look at the splitting nodes, and the logic used to partition the data at different layers, and more or less that are straightforward for human understanding. So you may not need separate layers for those. Decision rules is another one, which you can actually extract from decision tree models. That's actually a bunch of if-then statements, and straightforward to understand. Naive Bayes, if you remember from our Module 3 study of Bayesian classification, so naive Bayes one simplifying an important assumption that conditional independence, given the target, all the variables are independent. So that makes it easier to provide interpretation, or to make the underlying logic easier to be understood by humans. The k-nearest neighborhood is, it's not really, we don't train model in k-nearest neighborhoods. The decision is made during the application. So when you load the data, you look at the neighboring cases, and you make the determination based on the characteristic of the neighbors of that particular instance that you're predicting. But that fact that makes it easier to understand, so it doesn't require a separate interpretation layer or explanation layer. Okay, so all these are, if you remember, the different types of categorization of explanation methods. This is a modular level because, for instance, in decision trees, in a regression, we look at the weights, right? So that is one aspect of the model. So that's a modular approach, or a modular level, except the k-nearest application, because there isn't really a model in that aspect. Okay, I guess we have one more slide. This is actually the last slide. So, future of model explainability. As I started this lecture with the need statement, right? So we are deploying machine learning, automation, and AI solution in the various aspects of life in our daily chores. So interpretation is becoming more desirable and more necessary than before. So we will continue to advance in this area. As I said, this is an area still being explored, and new methods and explanation logic are being developed. So I would expect that this continue to develop. Of course, the application area is really a key factor in determining, how much interpretation, if any, is required for that application. If trivial application, you may not need, much of an interpretation, but more mission critical domain, safety critical application, that you would have to have interpretation. Okay, so the trend, and I've seen some new APIs, particularly for some complex model, black box models, they are providing a layer, interpretation layer, so you can easily provide some level of interpretation to the underlying logic of the model. Okay. As far as resources, I found this book, The Interpretable Machine Learning by Moeller. It's a very nice book. It's an online free book, and so I provided a link here. You can just have access, and if you're interested in the details of each of the things that I try to cover in this lecture, I get most of it from that book. Thanks for your time, and we will continue to cover model interpretability in the class discussion.